to another exciting video. This is your favorite tutor Mugdal Day, and today we are going to discuss June 2024 Unit 6. So without further ado, let's get started. Okay, number one, an organic compound A is a liquid and it contains two functional groups. Tests are carried out to identify A. Now, 1A says that test 1, a small amount of phosphorus 5 chloride, PCl5 was added to 2 cm cube of A, while in test 2 you can clearly see that aqueous sodium hydrogen carbonate is added to 2 centimeter cube of A. And the observations, you can clearly see that in the first one you can see that misty fumes were given off, and in the second one no visible reaction took place. Identify by name or formula the functional group identified by these tests. Justify your answer. Now, of course, test 1 is basically used to, identify or, determine the presence of alcohol groups in compounds. In this case, we can clearly see that misty fumes is given off, and if we more specifically speaking, that HCl gas has been given out. Okay, the reason why misty fumes was seen as one of the visible observations. So we can say that the compound obviously contains an alcohol group. Now the next part of the experiment involved test 2, where aqueous sodium hydrogen carbonate was added, and we saw no visible reaction. Now, of course, when you add sodium hydrogen carbonate, the purpose of this test is basically to determine the presence or the absence of carboxylic acid group. What happens is that you know that when carboxylic acid is present, it reacts with sodium hydrogen carbonate in something like this, and it results to the production of sodium acetate, whatever the alkyl group is, with water and carbon dioxide as a byproduct. So basically we can say that due to the production of carbon dioxide, the visible observation would be, if obviously the test would have been positive, there would have been an effervescence being seen. Okay, but since no effervescence has been seen, that means no visible reaction, so we can easily say that the compound contained an alcohol group, but of course it did not contain carboxyl group. So basically we can say that the compound contains an alcohol group or an alcohol functional group, but does not contain a carboxylic acid group or a carboxyl group. So we can write it down that the compound A consists of OH functional group, since the first test was positive. And we can say the next part is that compound A isn't a carboxylic acid because it doesn't react with sodium hydrogen carbonate. Okay, because if it would have been done, then we could easily determine the presence of a carboxylic acid, and we could say that compound A was a carboxylic acid. Okay, now moving on to the next one, they said in test 3 a few drops of A were added to 2 centimeter cube of Tollens reagent, which is basically nothing but ammoniacal silver nitrate solution. The mixture is placed in a warm water bath, and the observation was a silver mirror. You can see that. Identify by the name or formula the functional group identified by this test. Now, of course, we all know that Tollens reagent is basically an oxidizing agent, and it only reacts with compounds consisting of carbonyl groups, more specifically speaking, the aldehyde group, or this group right here. So since a silver mirror is observed when compound A is added to Tollens reagent, so we can easily say that the functional group present in compound A, that means the aldehyde group was present. So we can say that the aldehyde, or you can say that this group right here was present. Okay, now moving on to the next part of the question. It says compound A is non-cyclic and its mass spectrum has a molecular ion peak with mass to charge value 74. Now, of course, draw the displayed formula of two structural isomers of A using this information and your answers from A and B. Of course, in A and B, we have already identified the functional groups present in this particular compound, which is, of course, the alcohol group, and of course, the next one, the aldehyde group. So, of course, if we write down the two obvious functional group right here, and we here know that the molecular ion peak, or in other words, the molecular mass, the molecular ion peak in a mass spectrum represents the molecular mass of the compound, which is 74. We need to basically develop a compound structure which will provide a molecular mass of 74. So if we write the obvious elements already present, which we now know from the previous tests, from the previous question, so we have the alcohol group in one side, and then we have one of the carbons from the functional group of aldehyde and an hydrogen atom. With this, we are okay in our first step. We're done with our first step. So already we can clearly see that the molecular mass has been 2 oxygen, so it's like 16 times 2, and then you have 2 hydrogen, so 2, and with 1 carbon atom. So if you do that, you basically get about 32 plus 2 plus 12. Okay, so that would be sums up to 46. Okay, now 46, and if you subtract 74 minus 46, you get about 28. So more 28 gram per mole required. Now, of course, since compound A is non-cyclic and they have told you that it's a hydrocarbon, so we can easily say that the other elements must be a part of the alkyl group. So now the question is, how many carbon atoms are there in this alkyl group? So if we see, we can clearly see that if we use 2 carbons, then here you can see that 24, 12 times 2 is 24 gram per mole has been completed. I mean, has been, met by the required amount. So the only thing that's left is 4 more gram per mole. So how we can do that? Obviously, it will come from the 4 hydrogen atoms, two being connected with each respective individual carbon alkyl groups from the hydrogen atoms, basically. So now you can clearly see that the required 28 gram per mole has come from the addition of 2 carbon atoms along with the hydrogen atoms that they bring with their due to their addition with the whole compound. So with this, our compound A has been completed. Since they say 2 structural isomers, we basically now know that the molecular formula is same for isomers, but it's just that structurally it's going to be now different. Now, obviously, if I say that OH is connected with the third carbon right here, so we can just basically just change its position to by connecting it to the second carbon right here, and we'll easily get our second structural isomer. So we can just write it down as this, and we can just connect it with the second carbon right here, while we keep every other thing same. So with this, we got our first structural isomer, and that's our second structural isomer, with both of them having the same molecular ion peak of 74 in their mass spectrum. Moving on to the next one, they say the low resolution proton NMR spectrum of A shows 4 peaks with relative areas of 1:2 2:1. Now that the relative, areas of a low resolution proton NMR represents the number of protons present in each unique hydrogen environment. Well, it does. Now, we can clearly see that there's 1, 2, 3, 4 unique hydrogen environments by seeing the ratios, and we can see the number of protons present in each unique environment. So if we just write down the first structural isomer right here, for example, let's use the first structural isomer here to deduce whether our answers are correct or not. So if you just write down the first one like this, So we can clearly see that in one of the environment there's only one proton. So we can, and I mean actually two of the environments there are one proton in each of the environments. So we can just easily claim that this is one of the proton environment being represented by the high proton, the one proton present in the first part of the ratio. Secondly, if I say so, we can clearly see that this is another unique carbon environment, and that is another unique carbon environment, respectively being represented by the second part of the relative peak area ratio, and so that would be about B, and that would be C. While the last one will obviously be represented by the proton present in this environment right here. So we can just say that this is our D environment. Okay, so we can clearly see that the environments are basically being matched with the relative peak area ratio provided right here of its low resolution proton NMR spectrum. So we can easily say that the compound A structure, which we deduced in the first part of the question, it kind of makes sense. Okay, now let's move on to the next one. This is number 2. A series of experiments is carried out in an aqueous solution of chromium-3 salt. Okay, in experiment 1, to a sample of solution B, they said aqueous sodium hydroxide was provided. Okay, and it was added drop by drop until it was in excess. Okay, so the next part of the question says complete the table giving the observations you'd see when adding a few drops of sodium hydroxide. Okay, what happens when we add a few drops of sodium hydroxide? Precipitate gets produced, and the color of that precipitate is basically a grayish green type. So we can easily write that the color is grayish green precipitate is basically produced in the you can say it's being produced in the uh, reaction mixture. As an observation, we can see that when a few drops of sodium hydroxide is added, and the reaction, if you want the reaction to be seen, we can write it down as chromium H2O6 3 plus OH 3 OH minus. It tends to provide a precipitate of something like this. So this is the complex compound of the precipitate right here, the gray-green precipitate, this one, and water is produced as a byproduct. So this is our gray-green precipitate right here. Okay, now what happens when we add a few drops of sodium hydroxide solution in excess? So what happens is that the gray-green precipitate right here, it basically dissolves. So it basically dissolves something like this, and the OH minus ions which are in excess, it basically reacts and again leads to deprotonation reaction and results to the production of a very dark green solution. Now, since obviously the precipitate was grayish green, we are considering it's a dark green color. So obviously when it dissolves, the solution is going to turn dark green as well. So we can write it down as dark green solution is produced. Dark green solution form in both sense. And dark green solution, since deprotonation reaction is occurring, so obviously one of the H plus ion goes away, and we see a change in the ligand numbers of this complex, eventually producing this product right here, along with water as a byproduct. Okay, so this is our green, dark green. solution right here. Okay. State what you can deduce about the nature of chromium 3 hydroxide from the results of experiment 1. Now, of course, if you reverse both of these reactions right here by adding H plus ions, you'll be able to get the same reactants right here. You'll be able to get this one, and you'll be also be and eventually you'll get the chromium 3 salt, the green chromium 3 salt right here. So what does it mean? It basically means that it reacts with OH minus ions, as well as it reacts with H plus ions. So when it reacts with OH minus ion, it can act as a base. When it reacts with H plus ions, it can basically act as an acid as well. So we can say, it acts as an acid when it reacts with OH minus ions, and when it reacts with H plus ion, it acts as a base. So we already know that substances which can act both as a base on acid, they're basically known as amphoteric hydroxides. So we can say that it is the chromium 3 hydroxide right here is amphoteric. So we can write it down that chromium 3 hydroxide is amphoteric. Now, moving on to the next one, experiment 2, the state of 5 cm cube of hydrogen peroxide solution is added to the final mixture in A1 and heated gently. A yellow solution containing chromate 6 ions is produced. Explain the role of the hydrogen peroxide in this reaction. Now, of course, the reaction which we will tend to see, it's about something like this. You have CrOH3 basically reacting obviously it's chromium 3 hydroxide reacting. The final mixture is basically chromium 3 hydroxide in A1. So if you just then add it out with hydrogen peroxide right here, you tend to basically get about something like CrO42 minus is one of the products right here, and then you have water. Now in order to do it, balance it, you can just add 4 right here, 8 right there, and since there's to balance this out, we can provide 2 and 2 right here. So this is basically the balanced equation. Okay, so what is happening down here? If you look closely, we can clearly see that the oxidation number here is +3, and the oxidation number in chromium right here is +6. So what is happening? The oxidation number is increasing, right? So oxidation number is increasing, basically meaning that the chromate ions or the chromium ions are being oxidized, right? Because oxidation number is increasing. So if that's the case, then that means this is acting as a reducing agent. We can say that if you write it down in another side, this is acting as a reducing agent because it's getting oxidized by itself. That means that our common sense said that hydrogen peroxide is going to act as the oxidizing agent because that's going to get reduced. That's the most common logic, right? So we can easily write it down, the answer, that hydrogen peroxide right here is acting as an oxidizing agent. We can write it down that hydrogen peroxide is acting as an oxidizing agent as the chromium oxidation number changes from +3 to +6. Okay, moving on to the next part of the question, they said in experiment 3, dilute sulfuric acid is added to the UL solution formed in experiment 2, and the solution turns orange. Complete and balance the equation for this reaction. Now, when we basically add dilute sulfuric acid to chromate 6 ions, or in other words, CrO42 minus, we tend to get an orange solution, and the orange solution is nothing but Cr2O72 minus. And if we basically find the oxidation number right here, so we basically get about 2 sevens of 14 and -14 to be honest, and then have 2x right here. So if we just do that, that would be 12. So that's +6. I mean that there's no change basically we can say, but you can clearly see that the solution turns orange only due to the production of Cr2O72 minus right here. So, and the final product of it, the byproduct is water, because one of the oxygen comes out from here and it reacts with H plus, producing water. Okay, so this is the reaction. Now, if you want to balance it, we can clearly see that there are two chromium ions, so we can just write 2 right here. And it kind of balances the oxygen, because you can see there are 8, so there's 7, and there's 1 here, right here. So that, sums up to 8 oxygens in the right side. So the oxygen atoms are balanced, and we can see clearly, since there are 2 hydrogen atoms, we can just clip 2 in the left side as well, making the whole reaction balanced. Moving on to the next one, number 3, a group of students carried out an experiment to investigate the reaction between potassium manganate-6 and ethane diode ions in acidic conditions. Now this is the reaction, as you can see very clearly right here. This one. Now the steps are provided in this procedure. In step 1, you can see very clearly. Okay, so the first in the procedure, we can see that in 10 centimeter cube of potassium iodide solution, after measuring, it's kept into 8 conical flasks, and then in step 2, the student basically measured the 100 cm cube of ethane diode acid solution into a 250 cm cube beaker, and then we add 25 cm cube of potassium manganate 7 solution and 5 cm cube of sulfuric acid to the beaker, and the contents of the beaker are mixed very nicely, and the timer is started. And in step 3, when the reaction starts, immediately the 10 cm cube from the reaction mixture, from the total volume of the reaction mixture, is withdrawn, and it's added to the first conical flask containing excess potassium iodide solution. And like this, in step 4, for each conical flask, 10 cm cube of reaction mixture is removed, and it's added to a new conical flask containing the potassium iodide solution. And step 5, starch is used as an indicator in order to titrate the iodine formed in the conical flasks with sodium thiosulfate solution. So we have the equation provided for step 3 that takes place, the reaction that takes place in step 3, and the reaction that takes place for the titration in step 5 is shown right here. Now explain why step 3 effectively stops the reaction between manganate 7 and ethane diode ions. Okay, in step 3, what happens is that when the ethane diode ions basically react with potassium manganate, it's immediately when you withdraw it, you can clearly see in step 3 what is happening. The iodide ions is another reactant, which is basically helping the manganate 7 ions to basically react and getting all used up. So the whole point is here that if we want to stop the reaction effectively, all we want to do is basically, ensure that all the manganate 7 ions get used up. The only possible way is that if we withdraw in step 3 some volume of reaction mixture from the main beaker, and then add it up to the eight of the conical flasks individually. So what will happen is that the potassium iodide ions present in each conical flask, they're going to basically react with MnO4 minus ions, effectively causing all of them to get used up. So eventually the reaction is going to stop. Okay, so we can write it down. The iodide ions from Ki reacts with MnO4 minus ions rapidly, which causes all the MnO4 minus ions to get used up eventually and stop the and this causes stop the reaction. Exactly. So basically the whole point here is to allow the iodide ions to react with MnO4 minus ions, and allow all the Mn4- ions to get used up very rapidly so that the reaction stops. Moving on, in state number 2, they said state when the starch indicator should be added during the titrations in step 5, when the solution turns pale yellow, because we know that when iodine is produced, the solution turns pale yellow. When, to be honest, in more precisely speaking, when aqueous iodine is produced, the solution turns pale yellow. And when the solution turns pale yellow, due to the presence of iodide ions, or due to the presence of iodine, only then we should add the starch as an indicator, because starch basically reacts with iodine to produce the starch iodine complex, which results to the production of a blue-black color. This blue-black color allows us to provide, see a sharp color change for the titration ongoing in step 5. So we can easily write down as when the solution turns pale yellow, indicating the presence of iodide, or in other words, iodide or iodine formation. Okay, moving on to the next part. Students' results are shown. So this is the student's result. He basically took the measurements of the time and also measured the volume of sodium thiosulfate added in each minute, after each minute basically. Plot a graph of volume of sodium thiosulfate against time. So this is an example of the graph, and we can clearly see that in the y-axis we will put down or plot down the values of the volume of Na2S2O3 added, and in the independent axis, that means in the x-axis, the time values will be plotted, and then the data, according to the data values provided in this table right here, when we accurately plot the graph and then draw, we basically see a curve slanting downwards until the reaction stops down here after 7 minutes. Okay, so while drawing the graph, please ensure that the points, basically most of the points to be exactly, falls accurately at least near or within the curve, something like this. Okay, now let's move on to the next part of the question that said describe how the rate of reaction changes during this reaction. Now, using the graph, we can clearly see that the reaction was slow at the start, and then it starts to speed up, because we can clearly see that the volume of Na2S2O3 gets used up very fast, and then eventually the reaction slows down and stops. Okay, so we can write it down that the reaction was slow at the start, then it gains speed, and then eventually it slows down. Okay, so that's basically the description of the rate of reaction during the reaction that takes place for the reaction by and we basically interpret this from the plotted graph from the previous question. Now, moving on to the next part, explain why the rate of reaction changes in this way. Now, we can clearly see that one of the product right here is Mn2 plus. This is a transition metal, and we know that one of the greatest, characteristic, or one of the most important, characters of transition metal is that it can act as a catalyst. So during the reaction, as the reaction progresses, at first, the concentration of Mn2 plus is very low. It's the reason why its effectiveness is very low. But as the reaction progresses, what happens is that its concentration tends to increase, so this results to its increased effectiveness as a catalyst, which in turn results to an increase in the rate of the reaction as well. But Then again, what we see as a compromise is that what is happening is the MnO4 minus is also getting used up, and at one point, as the reaction progresses, its concentration decreases. So eventually, the amount of Mn2 plus being produced, its concentration tends to flatten. So at one point, what happens is that no more Mn2 plus ions tends to get produced. So we can say that its effectiveness tends to decrease again as well as a catalyst, and so this also results to a decrease in the rate of the reaction. So we can write down as that here Mn2 plus X as a catalyst. Initially, its production, or you can say its concentration, as a product is very less. But as the reaction progresses, its concentration increases, which in turn causes the rate of reaction to increase as well. Eventually, the reaction slows down as its production gets limited due to the reactants getting used up. Okay, so this is basically a very structured answer which basically provides a nice explanation about why the rate of reaction behaves in this way. Okay, now let's move on to the next part of our question paper. In number 4, it says this question is about the laboratory preparation of ester methyl salicylate, which is basically oil of wintergreen, also known as like that. Now the equation for this reaction is provided. You can see the salicylic acid reacting with methanol, and then methyl salicylate along with water as a byproduct is produced. Okay, and this is the procedure where in this step 1, both of these reactants are placed in a round bottom flask. Then sulfuric acid is added very slowly, obviously concentrated one, and then the mixture is heated gently under the flux for 45 minutes. And then in step 4, again it's cooled. The mixture is then, after cooling, the mixture is then poured into a separating funnel, and about 50 cm of iced water is added. The funnel is stoppered, shaken, and allowed to settle. The aqueous layer is discarded, while the organic layer is returned again to the separating funnel and washed with sodium carbonate solution right here. Again, the aqueous layer is discarded, leaving the crude methyl salicylate, while in step 7, the crude methyl salicylate is distilled and fraction with the boiling temperature range between 220 to 224 degrees Celsius collected. Now, the pure methyl salicylate is then transferred to a bottle and then weighed. Now, show by calculation that methanol is in excess in this preparation. Now, what we can do is that we can just easily at first calculate the moles of salicylic acid which are used up. So we can see that 20 grams of salicylic acid, and the MR value is provided, so we can just write it down as moles of salicylic acid used up, which is nothing but 20 divided by 138.0, which sums up to 0.1441493 mole right here. Okay, nextly, if we want to find the methanol right here, we need to know the moles of methanol. Now, of course, what we can say is that the volume of methanol is provided down here, which is about 100 cm3, and the density is also provided, which is about 0.791. So if you can find the mass and then just divide it with its smaller mass, which is about 30.0, we'll be able to get its mole. So if you just write down the mass of methanol right here, we know that density is equal to mass by volume, so it's going to be volume times its density, which is 0.791 times 100, since 100 cm of methanol was taken, which results to 79.1 gram. And obviously, like I explained before, the moles of methanol would be 79.1 divided by its molar mass, which is about 32.0, and that sums up to 22.4719 mole. Now remember, I gave 4 decimal places into right the first mole to ensure to keep your decimal places consistent while writing the moles for methanol as well. Now, if we just easily, we can clearly see here that the moles of methanol right here is extremely high than the amount of moles of salicylic acid being used. Right, so this easily say that methanol was in excess amount, and by how much? Now the question is by how much, right? So you can just easily multiply the moles of salicylic acid with its molar mass down here. So that sums up to about 4.64 gram of that's basically 4.64 gram of you can say that uh, that's basically 4.64 gram of salicylic acid, we can say that, right? So you can easily that's basically the molar mass, right? So you can just easily say that the mass down here is about 79.1 for methanol, so you can just also compare it in that way as well. That's 79.1 gram. The methanol is obviously an excess amount. You can see by comparing this values as well, the mass. So you can you can basically compare the moles, or you can just compare the masses of each reactant route here, and then prove that methanol is an excess amount. Moving on to the next one, that state the purpose of the sulfuric acid. Now, sulfuric acid, we all know in many common reactions, it acts as a catalyst, and it's also very important down here to ensure that the reaction basically, takes place at a faster rate. So, obviously, we are going to use sulfuric acid. So we can write that it acts as a catalyst. Moving on to the next one, draw a diagram of the apparatus used in step 3 when the mixture is heated under reflux. Heated under reflux, basically heat under reflux. So the apparatus we tend to use that is pretty simple. In heat under reflux, we tend to connect a reflux condenser. A reflux condenser is such that when you basically provide when basically what happens is that when the gas that evaporates from the round bottom flask, when you provide heat, it tends to condense back to liquid when it passes through the reflux condenser, only because we tend to provide water, we tend to circulate water around it. So water goes in this way while the water comes out this way down here, something like this. And it is connected with, of course, it is connected with a round bottom flask with, of course, 2 stoppers down here. So something like this, we can say. Tends to be something like this. Pardon the drawing. So the drawing is something like this, and of course the heat is provided from here. Okay, and then we have the reaction mixture inside. So what happens is pretty simple, in that in step 3 we can see the mixture is heated gently under reflux for 45 minutes, allowing the reaction to effectively take place. As the gas evaporates while heating, it then again condenses back, so that the unreacted reactants again react with the quickly, or you can say effectively, so that the reaction can go to completion. That's the whole point of heat under reflux in step 3. Moving on, they said in number D, describe how to wash the organic layer with sodium carbonate solution in step 5. So what we can do is that we can add sodium carbonate solution to the separating funnel, as you can see, as this said in step 5, that we can add it, and a separating funnel was basically used in order to return the organic layer and wash with sodium carbonate solution. So what we can do is that we can add sodium carbonate solution to the separating funnel and then stopper it, and then invert the separating funnel so that the reaction mixture gets mixed very nicely. And then you can just open the stopcock or the stopper and then release the pressure of the carbon dioxide gas which is produced during the reaction. Okay, this will basically allow the layers to settle down, the organic layer and the liquid layer and the precipitate layer to settle down as the pressure basically gets out when we open the stopcock in the second step. So the first step would be, it's pretty simple, is that you add sodium carbonate solution to the separating funnel, and the separating funnel looks something like this, if I say so, and we tend to get a tap right here. The tap is something like this, you can say, and this is it. So you add sodium hydrogen carbonate solution to the separating funnel. Okay, then you stopper it and invert it like this constantly, or shake it and or you can just write and shake it in an inverted manner. This will basically allow the reaction mixture to take place, or you can say the mixture to mix nicely. Okay, the next part is that you open the stopcock. You basically open the stopcock, or like this. This is the stopcock, to be honest. This is the stopcock. So you open the stopcock and, allow the release of the pressure produced due to trapped CO2. So the CO2 gets away, and this basically allows the layers to settle down. With, of course, the precipitate layer is settles down down, while the less denser one settles at the top. Moving on, they said a mass of pure methyl salicylate obtained was 14.1 gram. Calculate the percentage yield, giving your answer to an appropriate number of significant figures. Of course, the first thing that we're going to do is that we will calculate the moles of salicylic acid, which we have already done in the previous part of this question, which is about 0.14493 moles. So we can just write down the moles of salicylic acid, which is about 0.14493 mole. Okay. The next part is that the molar mass of methyl salicylate. We have to calculate the molar mass of methyl salicylate, which is, of course, if we do it from the provided structure right here. So we have about 6 carbon atoms with about actually 7, or 8 with these two, and we have 3 hydrogen atoms. So 3 times 6, 8 times 12. 16 times 3, and if we just calculate the number of hydrogen atoms, we have 3 right here, and then we have 1, 2, 3, 4. So 4 plus 3 is 7, so 7. That basically gives us 152 gram per mole. So we can just write down the molar mass down here. The molar mass of methyl salicylate is about 152 gram per mole. Okay, so the maximum mass we can calculate is pretty simple, because we can see that the reaction basically is taking place at 1:1 ratio. So the moles of salicylic acid being used up will be the amount of moles of methyl salicylate produced as a product. right? So we can assume that the moles of methyl salicylate is 0.14493. So we can say that the maximum mass could be produced of methyl salicylate salicylate. We can just easily multiply the molar mass with the moles down here, and that basically gives us about 22.029 grams, right? So now we know that the mass, we know that it's basically actual divided by theoretical, right? So the percentage yield right here, percentage yield formula is nothing but actual divided by theoretical times 100. So theoretically, we know 22.029 grams of methyl salicylate must be produced, but we obtained in reality 14.1. So if we just find the percentage yield, that would be 14.1 divided by 22.029 times 100. That would basically sum up to 64.0%. So the percentage yield is 64.0%. Moving on to the next part of the question paper, they say the label has come off a bottle known to contain ammonium salt, NH4X, where X is known to be a halide ion. Okay, fine. A student carried out an experiment to determine the identity of the halide X. The procedure has been, provided down here. Uh, describe in A1, they say describe how to carry out step 4. You should identify both how to perform the test and how you know all the ammonia had been evolved. We can see in step 4, the gas coming out from the conical flask was tested regularly until all the ammonia had been evolved. So obviously the gas here is ammonia down here. And we know that in our A-level course, the only alkaline gas is ammonia, which we have been taught. Right? So how do you basically determine the basicity or the acidity of a gas? Very simple, the litmus test, right? So what we do is that firstly we hold a rad damp litmus paper, obviously, over the mouth of the flask, right? Because this was carried out in a conical flask. Added. So when the gas basically evolves, and if you basically, hold the red damp litmus paper over the mouth of the flask, what will happen? What's going to happen is that it will turn blue. Now this basically indicates that the ammonia or the gas evolved was an alkaline gas. Okay. Now the question again does say that how you know all the ammonia had been evolved. So what we can do is pretty simple. If we just repeat until the litmus paper shows no color change, we can easily say that no more ammonia gas is being produced as a product, right? So this will basically ensure that all the ammonia have been evolved as well. Shows no color change. Okay. Now moving on to the next part, containers of ammonia gas have the following hazard warning signs. State these two hazards associated with ammonia. In previous Unit-6 question paper, we have already discussed about this, that this type of, hazardous warning signs indicate that the gas ammonia is basically corrosive. The hazard sign involving a skull basically indicates that it's toxic, or you can say it's poisonous. So we can say that ammonia is both corrosive for our skin and toxic for our health, or poisonous for our health as well. Give a precaution to reduce the risk when carrying out steps 3 and 4. It is assumed that safety goggles in the laboratory coat are used. So basically these two are omitted. So the other two we can say is that if we can carry out the experiment in a fume cupboard, that would be the best option, because that will allow the ammonia gas being produced to be enclosed in one single environment, in one single, enclosed chamber, keeping us, at a safe distance from where the reaction mixture takes place, or from the reaction environment involving the ammonia gas. So we can write it down that carry out steps 3 and 4 inside a fume covered. Nextly, they say that titer in step 6 is 26.80 centimeter cube of 1 mole per dm cube of hydrochloric acid. Calculate the molar mass of NH4X. In step 6, the entire contents of the flask containing excess sodium hydroxide were titrated with the given concentration of hydrochloric acid. Now they told you to find the molar mass of NH4X. So if you can at first find the moles of NaOH that reacted at the start, we can easily do the math because obviously we can see what's going to happen. What's going to happen is that we can clearly see that it is reacting at 1:1 ratio, and obviously the HCl is going to also react with NaOH at the same moles as well. So if we can find the moles of NaOH, so we can then find the moles of HCl. So we can then again just subtract it from each of the moles to get the moles of NH4X, because if we can find because that if we can get the moles of NaOH used up, we'll be able to get indirectly the moles of NH4X, because the mole ratio down here is 1:1, right? So after finding the moles, it's pretty easy to find the molar mass of NH4X, because we know the molar mass. I mean, it's to find the molar mass of NH4X because we know the moles plus we know the mass of NH4X produced as well. So at first, if we calculate the moles of NaOH at the start, that would be 50 times 1.00 divided by 1000. And you can clearly see that 50 cm per 1 mole of the chemical. So if you just multiply the volume with the concentration, we'll be able to get moles down here, and that would be about 0.05 mole right here. Again, if you find the moles of NaOH, I mean, what is it? The moles of hydrochloric acid being reacted will be basically the moles of NaOH at the end, right? So we can just write down the moles of HCl reacting. That would be what? Or you can say moles of NaOH at the end, to be honest. So that would be, they said the titer was 26.80, so we can just write down at 26.80 times 1 divided by 1000. That's the amount of volume of HCl used up, so that would be 0.0268 moles, right? Now, what is the moles of NH4X? So if we can just subtract it from both, if we subtract both of these values, we'll be able to get the moles of NH4X produced. So moles of NH4X produced would be 0.05 minus 0.0268. That would be 268. That would be about 0.0232 mole. So now we know the mole, and they basically said that here 2.27 gram of NH4X is produced. So now we know the mass as well. So the molar mass is now pretty simple. That is, you have to just divide the mass with the mole, 0.232 you just got, and that would give us about 97.845 gram per mole. So that is the molar mass of NH4X. Moving on to the next part, identify the halide X present in NH4X using your answer in B1. Right. Okay. So this is a little tricky question, but if we say so, what we saw down here, the molar mass is 97.845. Right. So NH4, if we just basically find the molar mass of this one right here, so that would be 14 plus 4, which gives us 18, right? And that means we'll be requiring a halide ion that would have a molar mass that would basically, by adding, that will have a molar mass of more than, if you see, it's about 97.45. So if you just subtract it, minus 18, we tend to get about 97.845 minus 18. That would be about 79.8, right? And the most closest halide consisting of this molar mass is bromine. So the selection of bromine would be a suitable one as a halide X present in NH4X. We can say bromine is most suitable as its molar mass is close to 79.9 approximately. Okay, so that is it. Okay, now moving on to the next part. Give a chemical test with the expected results. Confirm the identity of the halide in a sample of NH4X. Now that is pretty simple. The test of halides, what we do is pretty simple. That we, first of all, what you're going to do is that we're going to add silver nitrate solution to a solution of NH4X. And of course, dilute nitric acid is also required in order to ensure that no carbonate ions exist. Secondly, what's going to happen? The observation that we're going to notice, since for the test of bromine, a cream precipitate will be produced. Cream will be produced due to the formation of AgBr, silver bromide. Okay, if we move on to the next part, they say another student carried out the experiment but did not titrate all the contents of the conical flask in step 6. Instead, they transferred the contents of the conical flask to 100 cm cube of volumetric flask. Now, the solution was made up to the mark with distilled water and mixed thoroughly. 25 cm cube portions of the solution were placed in a conical flask and then titrated with 1 mole dm cube of hydrochloric acid. So now, what's the advantage and the disadvantage of this alternative to step 6? Right, okay. Uh, the first obvious advantage, we can see that you'll be able to do more titrations because you're basically taking out 25 cm portions of the solutions in conical flask. So the advantage would be that you'll be able to do more titrations. So if you're able to do more titrations, what you can do, you'll be able to get concordant results, or you'll be able to discard any sort of anomalies present. And concordant results basically mean that titers must have a difference not more than 0.20 centimeter cube, or sorry, dm cube to be precise. So we can say that you'll be able to perform more titrations, which will allow us to achieve concordant results by discarding the anomalous titers. So that's an obvious advantage. Now, of course, the disadvantage is that since 25 cm cube portions are taken, so a smaller volume of acid will be required during titration, right? So the volume of hydrochloric acid required will be less. So due to the smaller volume, we'll tend to get a greater percentage uncertainty in the calculated when the titers are basically calculated, and this will lead to a decrease in the accuracy of the whole experiment. So we can just write down is that the amount, a smaller volume of acid is required during titration. And so the titers will be smaller in amount, and this will greatly increase the percentage uncertainty, or percentage error to be precise, and so reduce the accuracy of the experiment. So that's the another disadvantage that we are going to basically face if we basically perform this alternate step instead of step 6. So with this, this paper, Unit 6 paper, is completed. And please like, share, and subscribe this video in order to get more engaging, exciting paper solving videos in the future. And that's it for today, people. Bye bye.